So, good morning, everyone. Welcome to the second day of IPEC. Today we have got, we start this day with invited talk of Wojciech Samotij. Wojciech Samotij comes from Wrocław. He got master's student at the University of Wrocław, and then he received PhD from University of Illinois at Urbana-Champaign in 2011, supervised by Joseph Balog. After a postdoc at Cambridge, he moved to Tel Aviv, and where he's now an assistant professor. He mostly works like on the boundary of what we usually see here on WG. It's not a structural graph theory or algorithmic graph theory. It's rather random graphs, extremal graph theory, additive combinatorics. So this is a bit different than what you usually see at WG. So the more I invite you to listen today. Wojciech also received, I think the biggest prize that Wojciech received was 2013 European Prize in Combinatorics for his works. So that's very short brief of Wojciech. So today Wojciech will be telling us about how to enumerate independent sets and how to count them, or how to look at independence in the graph. Just a few technical things. You can ask questions here, just to remind you. You can ask questions on chat on Q&A or raise hand. I will try to look whether anybody asks any questions, just to pass them to Wojciech and pass them to Wojciech, and please ask questions on the fly. We'll try to answer them. Also, we're recording the talk, and we'll put the talk on YouTube. So also, like when you're on this scene, you will be recorded and put it on YouTube. So be aware of that. So without further delay, please, Wojciech.
Thanks, Marcin. Thank you very much for the invitation. So as Marcin said, most of my research interests are somewhat on the boundary of the scope of interest here at the conference. So the topic I chose for today is maybe not something that I've been looking at recently, but I hope it will be interesting to you because it lies on the intersection. It concerns sort of graph theory, and it has an algorithmic flavor. So let me first introduce some notation. We'll be talking today about independent sets in graphs. So it's good to have a few pieces of notation. By the script I of G, I will mean the family of all independent sets in the graph G. And we'll be counting them. So little I of G will be the cardinality of the set. And now I sub M of G will be the number of independent sets which have size precisely M. Now the topic would be to estimate IMG for a given graph or a family of graphs G. Let's start with a trivial upper and lower bound that is true for every graph. So for the lower bound, note that if I take a largest independent set, which is alpha G elements, then each of its M element subsets will also be independent. And this gives me this lower bound of alpha G choose M. On the other hand, we have a trivial bound of the number of vertices choose M. Now what I'll talk about today is a way of improving this trivial upper bound, and the method I will present in many interesting scenarios can match the lower bound here, just given by considering all M element subsets of a largest independent set in many cases of interest, and I'll present a few examples. So why do we do this? The method I'll present was discovered twice in the 1980s, first by Kleitman and Winston in 82 and then Sapozhenko in 87. And since then, this so simple but powerful idea had plenty of applications. So let me mention a few of them. It was first used to studying graphs without 4 cycles. Also to studying independent sets in the hypercube, which in physics is sometimes called the hardcore gas model. It was also used to study sum-free sets and Sidon sets. So these are two topics in additive combinatorics, intersecting families of sets, and more lately, it was a helpful lemma for obtaining stronger lower bounds for Ramsey numbers. So as you can see, there's plenty of applications spanning several fields, and also all of these papers span 4 decades. So from the early 80s, and the most recent paper is 2019 plus. So people are still sort of interested in this method. And the reason why it has so many applications is that there are really many, many problems that maybe are not directly phrased in terms of independent sets, but one can translate them to a problem about independent sets in graphs or more generally in hypergraphs. So I think it's just something worth having in one's toolbox. Now, to motivate the statement of the lemma, let's try first to improve this trivial lower bound, which we obtained by considering all subsets of a largest independent set. Now, instead of looking for many independent sets in a large independent set, we could also look for many independent sets in a sparse set. So let me be more precise. Given a subset of vertices U and an integer m, suppose that the density of edges in the set U is asymptotically smaller than 1 over m. Now, let now R be a random subset of U with slightly more than m elements, m plus, say, 1% of m. Now, know that if we take the set at random, let's calculate the expected number of edges in the set R. So this is this expression, m roughly m squared over u squared, times the number of edges of U. And since the density of U is 1 over m, this number will be asymptotically smaller than m. So what does it mean? We take a set of roughly m elements, and the number of edges we see there is much, much smaller than m, so we can just remove one vertex from every edge, and we get an independent set of size m. So in particular, since this expectation is much smaller than m, then with probability close to 1, so a typical such set of size m prime will contain an independent set of size m. So by double counting, the number of independent sets inside U is U choose m prime divided by the overcount, because maybe I saw each m element set many times. And this leads to the following bound. So we roughly get U choose m independent set, assuming that we found a sparse set U whose density is at most 1 over m. Okay. Suppose we now reverse this density condition. It turns out that we can match the lower bound we obtained there from above. So to be more precise, let's assume that the density here, which I denote by beta, will be at least 1 over q times a logarithm of n over r. And we further assume that every subset of the vertices of G, which has at least r elements, has density at least beta. So the number of edges is at least beta times U choose 2, the number of pairs of vertices in U. Under this assumption, we can prove that give the following bound on the number of independent sets of size q plus r. So starting from this threshold value q, which will determine the density that we have to assume that every set of size at least r has, we can bound the number of subsets of size q plus r by n choose q times r choose r. And the idea here is that in applications, we take r somewhat larger than q, so that this first term, n choose q, doesn't matter, and we bound the number of independent sets by r choose r. So instead of having a bound of n choose r roughly, we have a bound of r choose r, if we assume that every set of size at least r is somewhat dense. So this is the statement, and the theorem is not very difficult to prove. And in the next few slides, I'd like to present the proof, because sometimes if you need to use it, it's better, instead of using the ready statement, it's just better to adapt the argument to your needs. So here's how it goes. The proof will be algorithmic, and you should think of obtaining an upper bound on the number of independent sets as a problem of efficiently encoding independent sets. So the idea of the proof is to describe an algorithm that as an input will get an independent set of the graph, here I denoted by I, which has at least q elements, and it will associate to it, it will produce a pair of sets, S and A, which are disjoint sets of vertices in G, with the following properties. First, S will be a subset of the independent set I, and the remainder of I will be contained in the set A. So the pair S and A will sandwich the set I from below and above. Moreover, S has only Q elements, and A has at most R elements, where R was the threshold for size of a set above which all sets has density at least beta. And now, how should we think about it? You should think of S as kind of a fingerprint of the set I. So we just sample some small set of elements which represents I. And the crucial idea here is that, of course, as this set A, I could just take I minus S, but the idea here is that the set A will depend only on S. So every set I will contain some small representative fingerprint S, and based on this fingerprint alone, we can build the set A, which is not too large, so that the remaining elements of I are contained in the set A. And what do I mean precisely that A depends only on S? It means that if we get two inputs, I and I prime, and the algorithm outputs two pairs, SA and S prime A prime, if the S's are the same, then also the A's must be the same. Note that the existence of such an algorithm already implies our claimed upper bound on the number of independent sets. So indeed, the number of independent sets of size Q plus R is at most the number of ways to choose the representative set S, which is N choose Q. And once S is given, it determines the set A. And from the set A, we need to choose the remaining R elements. So this gives us this capital R choose R. So there are at most N choose Q possible values of S. And given S, there is at most A choose R ways to choose the remaining R elements. And the size of A is guaranteed to be at most capital R. The main idea, so the key idea that allows to prove such a statement is to consider what I refer to as the max degree order of the vertices of a graph. So I hope that most of you are familiar with the degeneracy ordering of vertices of a graph, meaning we take a graph and we peel from it vertices with minimal degree always. Here we'll do something so complementary. We'll take a graph and we keep peeling off vertices with largest degree. In order to break ties between vertices that have the same degree, we first fix some arbitrary total ordering on the vertices. I will denote it by this curly less or equal sign. And here's how we define the ordering. The ith vertex in the ordering is the vertex with the smallest label in our ordering that has the largest degree in the graph G after we deleted the first I minus 1 vertices. So the first vertex will be some canonical vertex of maximum degree. We delete it, and then we again find a canonical vertex of maximum degree, and so on. And we order the vertices in descending order. So V1 is the vertex with largest degree, V2 is the vertex of largest degree in what remains. So just to illustrate it, suppose we have a graph G, we find some vertex whose neighborhood has largest size, and we label it V1, we take it outside. Now, with the graph with the vertex deleted, we again find a vertex with largest degree in this graph, we label it V2, and we remove it from the graph. And V3, and so on and so forth. Now, let me describe the algorithm. So the algorithm at all times will keep a partition of the set of the vertices of G into three sets, S and X and A. So where these S and A are the final sets we want to return, but they will evolve dynamically. Now, these letters S, X, and A should stand for selected, excluded, and available. So in the beginning, since we don't know anything about our independent set, all the vertices are available to be inside. So here's how the algorithm works. Suppose that we selected still fewer than Q vertices. Now, then we do the following. We order the vertices of A as V1 up to VA in the max degree order. V1 has the largest degree, and then V2 has the largest degree in what remains, and so on. Then we inspect our set I, and looking at the vertices of A, V1, V2, and so on, we find the smallest index I for which Vi is an element of our independent set. Then since the vertices V1 up to Vi minus 1 are not in the set I, because Vi was the earliest one, which is in I, then we move them from the available to the excluded ones. We move them from A to X. Furthermore, we move Vi, the selected vertex, from A to S. And now, so far, we haven't used anything about the assumption that the input is an independent set, so we'll do it in the last step. Since we know that Vi is in the independent set, it means that none of its neighbors can be in the set I. And therefore, the neighborhood of Vi in the set A, among the vertices that we haven't considered yet, we can move it from the set of available vertices to the set of excluded vertices, because no independent set that contains Vi can contain any of the vertices because they're neighbors. So let's now I claim that after this algorithm terminates, we have a pair of sets S and A with the desired properties. So note that certainly the set S has Q elements, and it's a subset of the independent set. And what we need to show is that A has at most R elements, and that the set I is contained in S union A. So let's analyze the algorithm. Now, in the first step, I would say it's rather straightforward to verify that ASX is always a partition of V of G. Note that in every step of the algorithm, we're just moving the vertices between the sets. We always move a vertex from A to either S or X. Second, at all times, S is a subset of I. Indeed, we only move to S vertices that are in I. And moreover, I and X have empty intersection, right? Because we only move to X vertices that we've already determined are not in I. And since XSA is a partition of the vertices of the graph, it means since I is disjoint from X, it means that I has to be contained in the union of S and A. Now, some meditation shows that in order to recreate the entire execution of the algorithm, one doesn't need to know the set I itself, but it's enough to know the set S. And just so to indicate the essence of the argument is that we only ever look at the smallest element in our ordering that belongs to the set I. And this is an information that we can recover based on the set S. If in the second line of the while loop I replace I by S, then the resulting output of the algorithm would be identical. So the crucial property here would be to show that the final set A is not too large, that it has at most capital R elements, as we promised. So to see this, let's analyze how many vertices are removed from A at every step of the while loop. Suppose that after some iteration of the while loop, the set A of available vertices still has more than R elements. If it has fewer than R, then we've already reached our goal. Now, in this particular iteration, I plus the degree of Vi in the remainder vertices are removed from the set A and moved to either S or X. So this I corresponds to the vertices Vi minus 1, and Vi. And the degree here is the size of the neighborhood, intersection of the neighborhood of Vi with the set Vi plus 1 up to Va. Now, since we picked, by the definition of the maximum degree ordering, Vi is the largest degree vertex in this induced subgraph of G's induced by the vertices Vi up to Va. So therefore, we can write this equality. And now, maximum degree is always at least the average degree. Now, what do we know about the average degree of this graph? We know that the set Vi up to Va has at least R elements. This was our assumption. And therefore, it induces in G, by the assumption of the lemma, a subgraph of density at least beta. Now, if I have a subgraph of density at least beta, it's equivalent to saying that the average degree is at least beta times the number of vertices of the graph minus 1. And therefore, this average degree is at least beta times A minus I. So adding these two together, we see that in every step of the algorithm, A loses a beta proportion of its vertices. Now, we'll do it unless the set A gets below this threshold R, every iteration will shrink it by a factor of 1 minus beta. So after Q iterations, it will shrink by 1 minus beta to the Q. Then this is at most E2 minus beta Q. And our assumption guarantees that E2 minus beta Q times N is R. So just to recap, since we were always trying to add a largest degree vertex to our set of selected vertices, it guarantees that at every such step, the number of vertices that we could remove from A, the neighbors of this vertex, was at least beta times A. So after Q steps, the set shrank by a factor of 1 minus beta to the Q. Now, so this completes the proof of the lemma. And in the remainder of the talk, I'd like to describe 3 sample applications of sort of increasing difficulty of the lemma in real-life combinatorial situations. So I chose maybe the simplest applications here, and that could be phrased also in simple language. So the first one would be an application of the lemma to count independent sets in regular graphs. So here we'll follow the presentation of Alon and Sapozhenko, some free sets, which is a result, again, of Noga Alon from 91. And finally, we'll use the lemma to estimate the number of graphs without the fourth cycle. And this was the original application of the lemma in the paper when it was first discovered by Kleitman-Winston in 1982. So let's move to the first example, which is independent sets in regular graphs. The following question was asked by Alon, Granville, and Kahn. This was in maybe late 80s. Namely, how many independent sets can an n-vertex deregular graph contain? What's the largest number of independent sets in a graph from this family? And if you think about this problem, it's not, so there's a natural guess that presents itself is to consider the graph to be a disjoint union of copies of KDD, the complete bipartite graph with D plus D vertices. So each such graph is a deregular bipartite graph, and we take disjoint copies of it. So the number of independent sets is we just choose an independent set in each of the copies. And since the copies are disjoint, any union of such independent sets will be an independent set of G. So we have this equality. The independent sets of G are independent sets of KDD times to the power of the number of such copies. Now, what is the number of independent sets in KDD? It's a bipartite graph. It's split into 2 independent sets of size D each. Each of them has 2 to the D subsets, each of them independent, so it's twice 2 to the D, but this way we counted the empty set twice, therefore I subtract the 1 here. And if you do the arithmetic, then roughly this is 2 to the power a half plus 1 over 2D times n. And what was proved by Alon and Sapozhenko is that this is essentially close to best possible. So if the regularity D goes to infinity, then the number of independent sets in a deregular graph can never be more than 2 to the power 1/2 plus something that tends to 0 with D times n. So the only discrepancy here is the rate of convergence of this error term to 0 as d tends to infinity. And let me just remark that using a very elegant entropy argument, Kahn was able to prove a sharp bound in the setting of bipartite graphs, which was then strengthened by Zhao. So Zhao reduced the case of non-bipartite graphs to the case of bipartite graphs. So now we know an upper bound which exactly matches our construction, which is sharp at least for n divisible by 2d. But this proof of Kahn and Zhao is a bit more complicated. It's a beautiful entropy argument, and on top of it, Zhao adds a beautiful combinatorial argument. However, it would sort of diverge from the topic of my talk, so let me just present the somewhat weaker bound due to Alon and Sapuchenko. So here we'll see the lemma in action. So let G be an n-vertex deregular graph. And let's recall the statement of the lemma. The lemma says that if we manage to show that every set U of size at least R induces a graph of density beta, where beta is this quantity log n over R divided by Q, then we can bound the number of independent sets of size Q plus R by n choose Q times R choose R. And maybe the only mysterious thing is, how do we verify this condition that every set of vertices of a given size induces many edges? And in the setting of deregular graphs, it turns out that this bound we will get for sets of size slightly bigger than a half by a simple combinatorial argument. So namely, let's look at any set of vertices U of size slightly more than a half. Let's count the edges that are completely contained in the set U. On the one hand, every vertex of U is an endpoint of some d edges. So there are d times U endpoints of edges that start in the set U. In the worst case, the other endpoints of these edges will end up in the complement of U. However, since the graph G is deregular, the complement of U, which has size n minus U, can accept only d times n minus U endpoints of these edges, d per vertex. Which means that the numerator here, du minus d times n minus U, must stay within the set U. So we have this many so pairs of endpoints that stay in U, and therefore, if I divide it by 2, I get a lower bound on the number of edges of U. Since U was slightly bigger than a half, by this sigma, we get a lower bound of 2 sigma d over n times n choose 2. And we denote this 2 sigma d over n, we let it to be our constant beta. Now, the rest is a technical calculation. We take Q to be the minimal such that beta satisfies the condition of the lemma, and we verify that it does. And how can we count now the independent sets? The independent set of size up to Q, we just count trivially. There are sets, just subsets of the vertex set of the graph. But starting from sets which are larger than Q, we can apply the lemma, which says that there's at most n choose Q subset times R choose R. And our R was chosen to be 1/2 plus sigma times n. And some asymptotic estimates give us the following bound. So here's, please don't worry if you don't follow the calculation. It's the most important thing was how to obtain this lower bound on the number of sets of edges spanned by a set of size U. And finally, we need to solve this optimization problem for sigma. And it turns out that square root of log d over d is the optimal choice to minimize the expression on the right. And we get the claimed upper bound of 2 to the power 1/2 plus constant square root of log d over d times n. So let me move on to a second application, which will use just the result of the first, and it will be slightly less technical. So here's an application of the lemma to the setting of additive combinatorics. I'll call a set of elements of an abelian group sum-free if the set contains no triple of elements x, y, and z such that x plus y equals z. An example of such a set would be, say, the set of all odd numbers. Since odd plus odd has to be even, then I cannot form a sum using three odd integers. Now, equivalently, a set A is sum-free if when I intersect A with any shift of A with an element of A, then the intersection is empty. So what does this imply? Since any shift of a set A has the same cardinality as A, then if A is a sum-free set, that inside the group G, I need to find at least two disjoint sets of cardinality the same as the cardinality of A and any of its shifts, which must be disjoint from A. And this implies that in any group, the largest size of a sum-free set is at most half of the elements. Note that this is tight, because if I take n to be even and consider the set of odd residues modulo n, then this set is sum-free. Again, odd plus odd modulo even is even. And this set has n over 2 elements, which shows that this trivial upper bound was best possible. So this is an extremal question one can ask about sum-free sets. But what we're going to discuss here is a counting question raised by Cameron and Erdős in the late 80s. So Cameron and Erdős asked, how many sum-free sets can we find in a group of order n? And note that the group Zn with n even contains at least 2 to the power of n over 2 such sets. And this is because any subset of a sum-free set is also sum-free. So if I take any set of odd residue classes modulo n, it will be sum-free, and there are n over 2 odd residue classes modulo n, so this gives me 2 to the power of n choose 2 subsets. Now, it turns out that one cannot do better in the group Zn or in any other abelian group for that matter. It was proved by Noga alone in 91 that every abelian group of order n can contain at most 2 to the power n over 2 plus a little o of n error in the exponent sum-free sets. In fact, for the particular group of Zn, one can choose that essentially all sum-free sets contain only odd residues and get a matching upper bound of 2 to the n over 2, but I'd like to also only discuss this weaker upper bound with this little o of n error in the exponent. So it's unclear looking at the problem that it has anything to do with independent sets in graphs. And the connection here is made by defining the notion of a Cayley graph. So given a set of elements of an abelian group G, we can define the Cayley graph script GS, of this group with the generating set S, as follows. The vertices of the graph will be all elements of the group G, and will connect two vertices with an edge if their difference is an element of S. However, since the definition of adjacency in a graph must be symmetric, then Z minus X could be in S, or X minus Z could be in S. So equivalent way of phrasing it is that XZ is an edge if Z minus X is either an element of S or an element of minus S, meaning X minus Z is in S. Now, observe that this graph is a regular graph. So what is the neighborhood? What is the size of the neighborhood of a vertex X? I can jump to a neighbor either by adding an element of S or subtracting the element of an element of S. So this is S union minus S choices. And the crucial connection here between independent set, and the sum-free condition is the following. Note that if A is a sum-free set and S is a subset of elements of A, then A minus S is an independent set in this Cayley graph. How do we see it? Suppose that the set was not independent, so we have some X and Z in A minus S, which are joined by an edge, which means we have two elements, X and Z, so that the difference between Z and X, or X and Z, is an element of S or minus S. And you can convince yourself, after rearranging this summation, that it means we have some element Y, such that X plus Y is equal to Z. X and Z are from A minus S, so they're in particular from A, and Y is from S, but S was a subset of elements of A, so we have a violation of the sum-free condition. So A is sum-free, S is in A, implies that A minus S is an independent set in this Cayley graph generated by S. So here's how we can count now the sum-free sets. First of all, if the set has at most square root of n elements, then we bound it by n choose A. This will be very, very small. Now, if the set has at least square root of n elements, then we can choose any representative set S here of size exactly square root of n and define the Cayley graph G sub S. And now the remainder of any sum-free set which contain the set S will be a set A minus S, which will be an independent set in the Cayley graph GS. And therefore, we can use the result from the previous slide. So this GS is a graph with n vertices, and the number of independent sets in any regular graph with n vertices is at most roughly 2 to the power n choose 2. And this is how we recover the theorem of Alon. And in fact, the question about the number of independent sets in regular graphs was motivated by this question of counting sum-free sets in abelian groups. And finally, in the remaining about 20 minutes of the talk, I'd like to discuss the final application of the lemma. And this is the original application due to Kleitman and Winston. And this is to the problem of counting the number of graphs that do not contain a 4 cycle. So this is a problem that is very close to my heart, because this is how I came to learn about the lemma some 15 years ago. Recall the definition of a Turan number. So the Turan number of the 4 cycle, EXNC4, is the largest number of edges in an n-vertex graph which doesn't contain the 4 cycle as a subgraph. Here, I don't mean an induced subgraph, just a monotone subgraph. A famous construction and an upper bound due to Brown and Erdős, Rényi, and Sós says that the largest number of this Turan number of the 4 cycle, the largest number of edges in a C4 free graph with n vertices, is asymptotically a half of n to the power 3 over 2. So the upper bound is an elementary counting argument, whereas the lower bound is a beautiful construction using discrete geometry. Now, since we've already answered this extremal question, we know the largest number of edges in a C4 free graph. The next natural question to answer is how many such graphs are there? How many do we have graphs with n vertices and no 4 cycle? Now, applying a reasoning similar to the reasoning in the first slide, where we estimated the number of independent sets, note that being C4 free is a monotone property in the sense that every subgraph of a C4 free graph is also C4 free, which means that we have at least 2 to the power of the Turan number of such graphs. On the other hand, by the definition of the Turan number, each such graph has at most EXNC4 edges. And therefore, we get this upper bound of n choose 2 choose m, which we sum over all possible values of m. Now, the lower bound by the theorem of Brown, Erdős, Rényi, and Schoch is 2 to the power 1/2 n to 3 choose 2, whereas the upper bound evaluates to something which differs by logarithmic factor in the exponent. So in this particular case, we get bounds which are really, really far from one another. And we're curious people, so we ask, okay, is the lower bound sharp, or is the upper bound closer to the truth? So since I don't want to write exponents all the time, let's take the logarithm of all the sides. So the previous slide says that the logarithm of this number is between 1/2 of n to 3 choose 2 and n to 3 choose 2 log n. It was asked by Erdős in the 70s 2 questions. First, can one improve the upper bound by eliminating this logarithmic factor? And the answer is yes, and this is what I'm going to present in the next few slides. This is the theorem of Kleitman-Winston. And a second question, perhaps if we manage to eliminate this logarithmic factor, maybe we can push it all the way to this elementary lower bound, and perhaps surprisingly, this problem is still open. So I know a lot of people who broke their head thinking about this question, including myself. If you want to sort of get into this topic of enumerating H-free graphs, I think this is an excellent problem to start. Now, the original application of the lemma is this result of Kleitman and Winston, which gives the following upper bound on the number of C4 free graphs with n vertices. So the log of Fn of C4 is at most 1.082. We won't care so much about the value of this constant, just a constant times n to 3/2. So we get a bound which is sharp to roughly a factor of 2. So again, our goal here is to show that the logarithm of the number of C4 free graphs is only a constant times bigger than the trivial lower bound that we got by considering all subgraphs of some largest C4 free graph with n vertices. Now, maybe one more reduction. It's enough to show that the ratio between the number of such graphs with n and n-1 vertices of order square root of n, and then we simply integrate this inequality to get the desired bound of n to 3/2 times a constant. Now, how do we relate the problem of counting graphs without a copy of C4 to a question about independent sets in graphs? I mean, here the connection is really unclear at first. Now, to make the connection, suppose that G is an n-vertex graph without a 4 cycle. Now, what we can do is to take some vertex V, and for reasons which will become clear later, we take V to be a vertex with smallest degree, and we denote by G sub V the graph obtained from G by removing the vertex V along with all of its incident edges. So it's a graph without the 4 cycle and with n-1 vertices. Now, the key observation is that if we look now at the neighborhood of V in G, which is a set of vertices in GV, it's an independent set, not in the graph GV, but in the graph GV squared, which is the graph whose edges are all pairs of vertices of GV which lie at distance 2. So the edges of GV are all pairs xy, so that xw and yw are edges of GV for some w. Now, why is the neighborhood of V independent here? Simply because if it was not independent, it means that we connected V to some x and y, but x and y have a different neighbor w, which means that Vxwy is a 4 cycle in G. So this reduction gives us the following idea how to derive an upper bound on the number of C4 free graphs with n vertices using a bound on the number of C4 free graphs with n-1 vertices, we may describe G by specifying the vertex V, then the graph G sub V, and finally the set Ng of V. Now, since G of V is a graph with n-1 vertices and no C4, and also by the choice of V, its minimum degree is at least the minimum degree of G-1, which is the size of the neighborhood of V-1, because V was the minimum degree vertex, we can bound the number of such graphs as follows. We choose the vertex n, there's n options, then we choose the graph GV, and there's f of n-1 such options, and finally, we choose the size of the neighborhood of V, this is D, and we choose D plus 1 vertices in the graph GV squared, but we know that they're independent, so this is I sub D plus 1 of H squared. Now, what is H squared? H squared is which is our GV squared, is a graph with n-1 vertices and no C4, and importantly, its minimum degree is at least D, because we knew that the minimum degree of GV by construction is at least the degree of V-1. So now, this is how this problem is reduced to the problem of counting independent sets in the graph H squared, where H is a C4 free graph with large minimum degree. So the only thing that I need to do here is to estimate this quantity. G sub nd is the largest number of independent sets of size d plus 1 in the square of a graph, which is C4 free and has minimum degree at least d. Now, to do this, we're going to apply the lemma. And we're going to count but we're going to separately count independent sets which are small and large. So first, define this cutoff between small and large, which is square root of n divided by a logarithmic factor. Now, if d is smaller than this, then we don't have to do much. A trivial upper bound is of just considering all subsets of size d plus 1 will give us a bound which is strong enough for our purposes, 2 to the power of square root of n. Now, in the complementary case, where d is at least square root of n times log n, what we're going to do is we're going to apply the lemma. And to apply the lemma, we let our parameter q to be log n to the 4, and our parameter r to be n over d. It is enough to show, I claim it's enough to show the following upper bound on the number of independent sets. n-1 choose q times r choose d plus 1 minus q. Since q is only logarithmic and d is almost square root of n, then only the second binomial coefficient here matters. So we get a bound roughly of the form r over d to the d. But now r was chosen to be n over d, so we have n over d squared to the d. And this function n over d squared to the d is an increasing function of d. And it's maximized when d was of order square root of n, but then the d squared cancels the n, and voila, we get the upper bound, which is exponential only in square root of n. So in order to obtain this upper bound on the number of independent sets, we only need to check that the assumptions of the lemma hold. Namely, we want to guarantee that every subset of vertices of H squared, which is size at least n over d, already induces quite a lot of edges in H squared. So again, this is the setup. Q is log n to the 4, r is n over d. And our H is a C4 free graph on n-1 vertices whose minimum degree is at least d. Now, by the lemma, we only need to show that every set of size at least r has density at least log n over q. How do we do this? what is the number of edges that h squared has in a set U? This is the number of vertices of U which are in distance exactly 2 in the graph H. So we're counting paths of length 2 between 2 vertices of U. Note that because the graph is C4-free, every pair of vertices of U can only be connected by one such path. And therefore, we can count the number of edges by looking at the middle vertex of the path. The vertex W is the midpoint of exactly the degree of W in U such paths choose 2. Now, by convexity, this sum will be the smallest when all the degrees of W into U are roughly equal. And by convexity, we get a bound of n, which is the number of vertices W, times 1 over n times the sum of all of these degrees. And this choose 2. Finally, since the minimum degree of H we assumed is at least D, the sum from the top of the binomial coefficient is equal to, first, the sum over all vertices in U of degree of the vertex in the graph H. And second, because of the minimum degree assumption, we have U vertices. Each of them has degree at least delta H, but delta was at least D, so we get D times U. Now, finally, plugging everything back into our lower bound on the number of edges, we get n times the binomial coefficient, which is D times U over n choose 2. Let's divide it by 2 over U squared. And this evaluates to this quantity, which in turn, using our assumption that U is at least R, is at least epsilon D squared over n. So we get a bound. Then D is at least square root of n over log n. We get a bound of epsilon divided by log n squared. And the only thing we wanted is log n over q. So as you see, this checks out. So just the key points here was marked with the exclamation mark. So we can count the number of paths of length 2 between 2 vertices of U using this convexity argument. And the second double counting idea here is that the sum of degrees of vertices into U is equal to the sum of the degrees of all the vertices in U. So just to recap, in 1982, Kleitman and Winston introduced a simple but very powerful method of counting independent sets in graphs. This is the lemma and the proof presented here. And this method has been rediscovered several times since, and it has found quite a few interesting applications in a range of problems. So if this topic interests you, then several years ago, I wrote a survey about the method, which is available on the archive. And let me also mention that this method of enumerating independent sets in graphs has recently been extended to the setting of hypergraphs. Unlike the set of graphs, so sometimes we need to struggle very hard to translate a problem in combinatorics to a problem about independent sets in graphs. But if we want to encode it as a problem about independent sets in hypergraphs, then the setting of hypergraphs gives us a lot more expressing power and flexibility. And if you're interested in reading on that, I can refer you to a survey paper I wrote together with Yoshi Balog and Rob Morris. It's also available on the archive. And since it's almost 10, let me stop here and thank you for your attention. Thanks for listening.